Today we're going to be talking about the countercurrent exchange mechanism. And the countercurrent exchange does just that. It exchanges things using a continuous concentration gradient. In order for things to be exchanged or diffused, we have to have a lot of something in one place and less of something in another place. For example, we might have a lot of oxygen here and less oxygen over here. And that allows oxygen to diffuse from where there's a lot to where there's less. And that's what the countercurrent exchange mechanism is all about. It's about creating that concentration gradient, that difference in concentration over a vast area. So let's go ahead and talk about this. The countercurrent exchange mechanism can be used in a lot of different places. For example, it can be used to exchange heat when we're talking about the legs of birds or the legs of certain mammals like foxes. It can also be used to exchange ions in water in the kidneys. It can also be used in terms of gas exchange in gills. And that's what we're going to talk about today. We're going to talk about using the countercurrent exchange mechanism to exchange gases in the gills. So let's go ahead and start there. The first thing I'm going to do is draw some gills. So here are my gills. This is just going to be a very general diagram of some gills. And I'm going to draw this nice and thick right here. Nice and thick. And this thick structure here is going to be a gill arch. And the gill arch can be made of bone or cartilage. And the gill arch is going to have gills attached to it. In fact, I'm going to make these gills nice and red because these gills have an excellent blood supply. In fact, this whole thing is a gill. These are gill filaments that are attached to the gill arch. And they have a very, very rich blood supply, just like your lungs do. The reason is, in order for diffusion to occur, we need to get the blood in the water, in case of gills, or the blood in the air, as close to each other as possible. So we want a very, very vascular gill here. Now, these are gill filaments. Each one of these finger-like projections are referred to as gill filaments. And I'm going to take one of these gill filaments and I'm going to enlarge it. And I'm going to use black to draw this gill filament. And it's a long finger-like projection. That's my gill filament. That's one single gill filament. And I'm going to draw some flaps of skin on my gill filament. I'm going to put some shading in there so you can see the flaps of skin. Let's draw a couple flaps of skin. And these flaps of skin obviously have names. Let's give it a name. It's called lamella. And these lamella, these flaps of skin, are going to serve to increase surface area. Because anytime gas exchange takes place, in fact, anytime diffusion takes place, whether that happens in a gill, whether that happens in your lung, whether that happens in your intestinal tract, it's all about surface area. And nature's going to find a way to maximize surface area. So by adding these lamella in here, we're going to increase the surface area of this gill filament, and therefore more diffusion can take place. Now the next thing I want to do is I want to put some water going over this gill filament. And the water just doesn't go any direction. It's going to go a certain direction. So the water is going to go this way. I'm going to make the water go this way. Let's go ahead and label that water, H2O. And let's suppose that that water is 100% oxygenated. And I'm just making up some of these numbers here. It's 100%, meaning it contains as much oxygen as it possibly can. 100%. 100% oxygenated. And again, I'm just making up these numbers. And as that water moves over the gill, obviously oxygen is going to get removed from that water, and this number is going to go down. Now the next thing I want to do is I want to draw some blood vessels here. because that's where the diffusion is going to occur, between the blood in the blood vessels and the oxygen in the gills. So I'm going to add some blood vessels in here. So there we go. And two things can happen here. We can either have blood and water going the same direction, or we can have the blood and the water going opposite directions. I'm actually going to talk about both of them, and then we're going to pick one in the end, the most efficient one. So the water's going this way. In this particular example, I'm also going to make the blood going the same way. And when the blood and the water go the same way, that's going to be called concurrent. Concurrent exchange. Now, let's suppose that the blood contains oxygen, which it does. And again, I'm going to throw out a number. Let's suppose that that blood is 60% oxygenated. This blood just came from the body, from the organs and the muscles, and they used up a lot of the oxygen. So the oxygen's a bit low in the blood, and that's why the oxygen came to the gill in the first place, to get more oxygen. So we've got a concentration gradient here. 100% of oxygen in the blood, 100% of oxygen in the water, 60% of oxygen in the blood. We've got a difference in concentration, and we know things want to diffuse from where there's a lot to where there's less. So oxygen's going to diffuse from the water into the blood. And the carbon dioxide is going to go the opposite way, from where there's a lot in the blood to where there's less in the water. Now, what's going to happen here is diffusion begins to occur across this gill filament. Very quickly, we're going to come to equilibrium. That means the concentration of oxygen in the water and the blood are going to be the same. And whenever you have the same concentrations, diffusion, or at least net diffusion, isn't going to take place. And that's one of the problems with concurrent exchange, is that very quickly we're going to come to equilibrium and gas exchange is going to stop. So at best, we're going to have a partial exchange of gases here. And that's not a good thing. Let's go ahead and write that down. Partial exchange of gases. And when I say gases, I'm talking about oxygen and carbon dioxide. Now let's talk about the countercurrent mechanism over here. Countercurrent exchange. And the word counter means opposite here. So things are going to be going in opposite directions. So I'm going to have the blood coming down in this case. And again, the blood, let's throw out a number there. Let's say the blood is 60% oxygenated. And the water is 100% oxygenated. And we've got the blood and the water going in opposite directions. Now what that's going to do is it's going to prevent equilibrium from happening here. So it doesn't matter at what point we are in this gill filament, the blood and the water, the oxygen and carbon dioxide concentrations are never going to come to equilibrium. That means that we're going to have a continuous concentration gradient across the entire gill filament. And we're going to have much, much, much more complete gas exchange take place. And that's what nature likes. Nature likes efficiency. So with the countercurrent exchange, we're going to have more complete gas exchange. And really that's what the countercurrent is all about. The countercurrent ensures that there is going to be a continuous concentration gradient across the entire gill filament. So one more time, the claim to fame that the countercurrent mechanism has is it allows a continuous concentration gradient to be occurring across the entire gill filament. And that doesn't happen with concurrent. We start out with a concentration gradient, but very quickly we come to equilibrium, and as soon as we come to equilibrium, gas exchange, at least in this case, stops. And that's it for the countercurrent exchange mechanism.